So this is the kernel. Okay. Yeah. So you can see. Okay. Yeah. This first parallel updating all the even size, and then do the parallel updating all size. Okay. Yeah. So let me go to the sample code. Okay, and then I would switch to the another screen. Okay, so let me stop this and then switch to another terminal. Okay. So okay. You can see there's using 2D 1 GPU with the global memory version 1, version 2, and version 3. Okay. So let me first go to the version 1. See you. Let me use the full screen. Okay, yeah. So you can see I have most all document in details. Okay, so you can read the code. Okay, without any difficulty. Yeah. So the even odd, okay, is also called a checkerboard. Okay, because this looks like the check even, because the even or odd. Okay, you can regard it as the black and white. Okay, so it looks like the checkerboard. Here, the random number, I have used the GSL MT19937. Okay, so, and now this is the kernel. Okay, so in this kernel, okay, I will first go over the even size and do the updating. Okay, yeah, okay. And then after doing that, I do the synchronize. Okay, yeah, yeah. So the all the threads, okay, in one block is synchronized. Okay, but however, this syn thread, okay, does not guarantee all the blocks are synchronized. Okay, you see, yeah, syn thread is only synchronize all threads within one block. Okay, but not does not have no effects to synchronize the threads between two different blocks. Okay, so it could happen. Okay, one block already complete the simulation. The other block, okay, has not completely finished it yet. Okay, so yeah, so the synfet, okay, is not a global synchronization, but only the all the threads within one block, okay, are synchronized. Yeah. Here, I have the detailed explanation about this. Okay. Yeah. Only apply to all threads in a block, but not all threads in the grid. Okay. So not all blocks are synchronized. Okay. So now the issue here, okay, actually it's not a big issue, okay, but just it could happen, okay, if you do simulation, okay, yeah, with the same seed, okay, but they may not necessarily get exactly the same result, but both results are correct, okay, yeah, physically are correct, okay, but they are not exactly the same, okay, so the results are yeah, simulated result, okay, yeah, both of them are correct, okay, but they are not exactly the same, okay, because both results, of course, have subject to various, say, statistical error, okay, as well as the systematic error due to the autocorrelation. Okay, I will talk about this later, but they are not exactly the same. The reason is that, okay, yeah, in these two different simulation, since not all blocks are synchronized, so that means some blocks, okay, may be updated differently, a little bit differently, okay, but then they all satisfy the detail balance, okay, so all these simulations are okay, but just not exactly the same, okay. I will show you. So one way to avoid this problem is update the even size and odd size within two separate kernels, okay. So with two separate kernels, that if I finish all the updating all the even size, and then I exit the kernel. After I exit the kernel, then all threads are synchronized. All threads of the entire grid are stopped, okay? And then I update all the odd size. Okay? So in this way, this is the version 2, okay? So with the version 2, then I would get exactly the same result if I start with the same random normal generator seed, okay? So this is the version 2 of the code. There's another way to overcome this issue, okay, is use the cooperative groups, okay. Cooperative groups means that then I can do a global synchronization, okay. All blocks and all threads are synchronized, okay, and it is available for the GPU, okay, with the compute capability bigger than 6.0, okay, and also compiled with the CUDA 9.1 or after, okay, yeah. So there's the version 3, okay. So there are 3 versions, okay, and yeah. So for the first version, version 1, then is the update the even size and the odd size, okay, put in the same kernel, okay. So in the same kernel, you can see, okay, after you update all the even size and then synchronize the thread, but this synchronization only affects the all threads in one block, okay, but not all blocks are synchronized, okay. But then you go to the odd size, okay, then you update some of the CPUs, some of the threads, okay, in some blocks, okay. So yeah, they already finished the even side updating, and then they will go to the odd side updating, okay. While some other blocks, okay, yeah. So this here, yeah, this not all synchronized, okay, may cause a slightly difference, okay. Yeah, the results, okay, yeah. So I go to the odd size and then do the updating, okay, update the odd size, yeah. Okay. So that means this is the updating the odd size and the even size are in the same kernel, okay, yeah. And you can see here everything else quite similar to the CPU code, but then for the GPU related features is the okay, here. I also use these two declare some of the you have used the constant memory, okay? The constant memory, okay, here, FFW here. So since every time I have to look up the labeling sites, okay, I have to know this array forward or backward, okay, in order to take into account of the boundary condition, okay. So this forward and the backward L array, okay, since it's used frequently, okay, it's better to put in some memory which I can access that very fast instead of the global memory. So since this array is a constant, so I can just put it to the constant memory, okay. So this is the command how to copy this data, okay, FFW to the FW, okay, to the constant memory, okay, of the in the GPU, okay. So here I have in the beginning I have to declare this constant memory, okay. Yeah. Yeah. Here, this is the forward index and the backward index, okay. That is in the system memory, in the CPU memory, okay. But then this data is copied to the FW and BW, okay, in the constant memory, okay. Yeah. Such that, okay, it can be accessed very fast. And this is the spin, okay, in the host memory, okay. And then this is the random number, the sets of random number, which is needed, okay, for a simulation, okay. So generated and then transfer to the GPU, okay. And the rest of the input are the same as the CPU, okay. And then I have to assign the block size, okay. So how many threads in TX and TY per block, okay. And then so this is the thread, okay. How many threads, okay, TX and TY. And then I know what's the grid size, okay. So how many blocks in X and how many blocks in the Y direction, okay. And this is the hot start or cold start. So this is the memory allocate, the spin, okay, and the random number, okay, in the device, okay. So this is the why there's a D underline spin and a D underline RNG, okay. And then copy the spin configuration to the device memory. So first, just pin out the exact solution with the input temperature, okay, and the volatilization. So, and then this is a simulation result, okay. So begin the simulation. So here, set up the timer, create a timer, and do the timing, okay. So for a thermalization, okay. So this is the kernel, okay, Metro GMEM, okay. So this is the using Metropolis, okay, and then using the global memory, okay. This is the kernel, okay. So you can see, okay, this kernel serves the purpose of doing the one swap or over the entire lattice, okay, updating, okay. So this is the thermalization is so many swaps, okay. So just go through all the swaps, and each swap at each time I have to call the kernel, okay. And then do the pin out, okay. If the and after thermalization, then I begin the the measurement. Okay, so here is the, yeah, every time I generate n as so many random numbers, and then send to the GPU, okay, and then call this kernel metro, okay, to do the updating of the all spins, okay, of the lattice. Yeah. If the swap numbers uh, coincide with the measurement interval, then uh, I copy the spin configurations, okay, from the device to the host, and then uh, the host will use it for doing the measurement of the magnetization and also the energy, okay, and also the pin out the results. Okay. And then if the swap number is equal to the display interval, okay, then just pin out the total averaged energy and the averaged magnetization. This is the energy density and then the magnetization density. Okay. And if the swap number is bigger is equal to the backup interval, okay, then you would save the spin configuration. Okay. And then okay, and finally finish all the entire simulation, and then finally also pin out the exact solution again for comparison. Okay, so now I can stop the timer and then say to get how many gigaflops. Okay, yeah, and finally destroy the timer. Okay, and then feed the random number generator, and also the device, feed the device memory, okay, and also feed the host memory, okay, and then that's it. Okay, so there's stop. Okay, so the entire code is uh, quite straightforward. Okay, and yeah, self-explanatory. Okay, and this is the exact solution here. Okay. Any question about uh, the simulation code version 1? Hmm?
Uh, uh,
Yes. Yes.
Professor, could you remind me in the flops, how does the seven come up?
Okay. So this is time. Okay, is the milliseconds. Okay. Yeah. So
Yes.
this is the GPU time, processing time. How many milliseconds it has spent in the simulation? Okay.
Mm-hmm.
And then but how many floating point operation has been uh, has been used. Okay. So for each, since I have to go through that many swaps, okay,
Mm-hmm.
and each swap, okay, I have to go through each site, okay. So how many sites? So this is the total number of sites, okay.
Mm-hmm.
And then each site, how many operations you have to use? There is a 7 floating point operations.
Okay.
Now, so you can count this 7, okay, okay, yeah. Go back to the code, and then you can count how many operations it involved. So it's 7.
Okay. Okay. Thanks.
Yeah, okay. Any other questions? Yeah. Okay. Now let me do the simulation. Okay. So make yeah, make okay. Now G1 here, the CMD, okay, job control, okay. The initial directory, okay. If you run it in your home directory, then you have to give it correctly, okay. What's the directory, okay. Yeah, you are working, okay. So you just PWD, and then you know you are working directory, and then yeah, use it here, okay. Okay. So this I have the version 1, version 2, and also the CPU output. Yeah. Last time I think the CPU output was not correct. Okay, but now it has been fixed. Okay, you can see. Okay, output C. Okay, so you can see the timing. Okay, here. Okay, and then this are so many milliseconds. So it is only 34 seconds. Okay, and the input ladder size here. Input 1 CPU. Okay. So this is the 256. Okay. Yeah. So this is a very large lattice. Okay. 256 by 256. Okay. And the number of swaps for femorization is 1,000. And I only take 1,000 measurement. And each measurement is separated by 10 swaps. Okay, for the display, okay, it's 100. That display is not important because it's the only intermediate result. Okay, and then the interval of saving the spin configuration. Okay, yeah, and this the J over T. Okay, is 2.4. Okay, and monetization is 0. Okay, and since 2.4 is above the critical temperature, above the phase transition, so it is better to use the random hot start. Okay, that means the random start. Okay? So the result was in the output. Okay, output 1 CPU. Yes. Okay. So you can see. Okay, this is the output. Okay, here. Oh, here is a 100 right in. Yeah, 256. Okay. Yeah, I can do it with the 256. Okay, maybe I should change it to. Then here, a input one GPU. Okay. 2, 4. Okay. Yeah. So this is the block size for the even odd scheme. Okay. So I use the 4 and 8. Okay. Yeah. So you can use 2 and 4, or and yeah, different block size may give you different performance. Okay. So yeah, let me also change the input 1 CPU, okay, to 256. Okay. And yeah, so and I just remove the output CPU. Okay. Yeah. And okay. So now G1 here. So this is the for the CPU. Okay, so I just submit this job. Okay, control submit CMD G1. Okay, so now I submit a job to do the simulation with the CPU. Okay, so yeah, this should take a little bit longer than 100 by 100. Okay, So and you can see, yeah, okay, it should start soon. Okay, yeah. Now is initialization. Yeah, now it's running. Okay, so it's running in the node 218. Okay, so host is the 218. Okay, but since there's a two nodes. Okay, so I can submit another job. Okay, with the GPU. Okay, and then it would be running in another node. I hope. Okay, yeah. Now, if running on the same node, then it may not be too fair for the CPU simulation. Okay, yeah. So it's better to have just one job in a for a CPU, and then the other job, okay, is a GPU. Okay, is in another node. Okay, okay, yeah. G1. Okay. Now, see with okay, that seems already finished. Okay, that one CPU always all one. Okay, let me see. Okay, so here's 256. Okay, so there's the how much. So about 38 seconds. Okay, so now let's see how much time it takes for the GPU, one GPU, or done already. Okay, so you see it's quite fast. This one, all one GPU version 1. Okay, so this is not much faster. Okay, you see, this is 21 second. For the CPU, about 38 seconds or so. Okay, and you can see the result. Okay, the result is yeah, the energy density is quite close to the exact solution, and the magnetization, okay, is very small, but cannot be zero, exactly zero. Okay, because it's yeah, uh, finite size, finite lattice. Okay, and they are not there's some incomplete cancellation. So the result is non-zero. Okay. Yeah. Um, yeah. This is just a rough. I mean, just the average. Okay. It does not give you any error. Okay. If you go to the error analysis, this may turns out to be plus minus or about yeah 10 times 0.00 1 or 0.002, 0.005. Okay, then that means this result is compatible to 0. Okay, if since the error is that size. Okay, so you have, yeah, this only is for the visually estimate. Actual estimate you have to say from the data. Okay, from the data to you see there's a using there's a data file. Okay, so the spin configuration. Okay, and then this the spin configuration saved. Okay, and then you have to read this spin configuration and then do the measurement again. Okay, and then do a detailed data analysis. Okay, yeah. So um, any question? Okay. yeah, let me grab the time, grab the gigaflops for the time. O1 GPU version 1. Oh. Okay. So I should grab the processing time. That was a earlier one. Okay, so this is the latest one. Okay, yeah, and okay, so this is the one not even a factor 2 faster. Okay, less than a factor 2. Okay, so about 1.8 or so. Okay, speed up. Okay. Okay. And the results are, both results are compatible with the exact solution. Yes. Okay. Now let me look at the code for of the version 2. Okay. Okay. Now you can see the kernel. Okay. This is the kernel for even size update. Okay. And there's another kernel. Okay, for the odd side update. Okay. So this is the odd. This is even. Okay. So this is that means that I separate the updating of the even side and odd side into 2 different kernels. Okay. And then in the main code, okay, in the main code, then I have to call these 2 kernels successively. Okay. Yeah. Yeah. Here you can see. First, I call the kernel, update the even size, and then call the kernel, update the odd size. Okay. Yeah. Then yeah, you can see. Okay. Yeah. Then you will avoid the issue of the yeah 2 different ones with the same random number generator may not get exactly the same result. Okay. Yeah. So maybe I should do the simulation with the version 1 once more, and then you can see the result of the simulation result is not exactly the same. Okay. So let me yeah, the input file, you see the input file one GPU. Okay. So the seek is always 1, 2, 3, 4, 5. Okay. So everything else exactly the same input file, the same seek. Okay. So if I do it do the simulation once more, okay, then I should get exactly the same result. Okay. Yeah. So completely reproducible. Okay. But actually it's not. Okay. I will demonstrate this. So I just submit the job once more. Okay. Let me see. Yeah, with the same input file. Okay. Okay. Second. Okay. Second here means the output to the second, and then I can look at the results and compare it. Okay. Actually, if I do not use different name, okay, then it just append to the same output file. Okay. So, but sometimes it could be confusing. Okay. So I just change with the different name so that we know exactly which is the first one and then which one is the second one. Okay. And then I have to erase the first the one with the oh, I only want to erase the previous one, okay, and keep the one which I have just submitted or simulated today. The one with the 29 second. Okay. Okay, so this is the one I just had today. Okay. Now let me look at whether the job has been finished or not. Oh, done. Okay. So there's another output is this. Okay. So you can see the version 1, second one. Okay. So after this simulation, I have after I do the measurement for 1,000 measurement. Okay. So this is the final accumulated average. Okay. And now I just grab 10900. Okay. R1 of the one GPU version 1. Okay. Okay. So you can see the result here. The result is the second one here, and this is the first one. You can see this different. Okay. You can see clearly. Okay, they're different. Okay. And also the processing time is different. Okay. Yeah. And the processing time different. Okay, may be due to different CPU node. Okay. Different CPU node. Okay, may have a different different performance. Okay, maybe due to the system itself. Okay, not the GPU card. Okay. So so grab the processing. Okay. So this is the first one process. Okay. So this is the first one, and this is the second one. The time, okay, is just a 3-second difference. Okay. And also the accumulated average are different. Okay. You see? Yeah, for the monetization, you see it quite clearly. Okay, they are different. Okay. So this seems a little bit Oh, okay. Yeah, although, okay, both should be consistent with the exact solution. Both are correct, okay. But yeah, we don't, no, we are not very happy with that, okay. So let's go to the version 2, okay, with the even side updating first, and then to update the second odd side, okay, separately, okay. Yeah, rather than in the same kernel, okay. So let me, okay, go to the, okay, choose this, okay, with the version 2, okay, yeah. Okay. And then let me double check the file. Oh, G1 is the same, okay, so okay. Oh, G1. Okay. So this is the first one, okay. Let's look at the, but then remove it. Version 2. Okay. Yeah. And then I don't know, they should, yeah. You see, it would create output file anyway. So version 2, okay. So I just removed the one in the previous one, okay. So this is the simulation just doing today, okay. Yeah. Finished, okay. So this is the 21 second, okay. And yeah, so this, you see, for this one, okay, you see the smaller, okay, but then you don't know the error, okay. Actually the error may be just more or less the same as this value, okay. So that means the is consistent to 0, okay. Yeah. Now let me do it again, okay. Do a same input, okay, and then just the, and then with the second, okay, second, so that I know this coming from the second one. Okay. No. Ah, okay. Okay, now he's doing the second one. Okay. And you only take 20 seconds or so, 22 seconds or so. So it won't be too long. Okay. Now, yeah, it takes some time to initiate. Okay. And this initial time can be, I mean, the system, the condo, okay, characteristic can be adjusted. Okay. Yeah. Okay, 18 seconds. Okay, so soon, yeah, should finish now. Oh, how come? Okay, done. Okay, now, so one GPU version 2, second one. Okay, you see? So the second one is now let me get the grab the 10900 of the whole one GPU. version 2. So this is the output from the first one, okay? You see, both results are exactly the same, right? There's you can reproduce the same result, okay, by the same initial seed, okay. So this is the yeah, I mean the version 2, okay, is the what usually you do a simulation in the CPU, then this is exactly the same thing you expect, okay. Yeah. Okay. Yeah, but for the version 1, okay, if you put both kernels, okay, I mean both updating right after the event updating, then maybe some of the not all blocks are synchronized. Okay, not all threads are synchronized. Then some blocks may start earlier. Okay, then you may have something different. Okay, so there's some unpredictability of the version 1 simulation. Okay. Any questions about this, the version 2? For the version 3, okay, I think I just skip, okay, you can read the details, okay, yeah. So I think version 2 should be sufficient for getting the Monte Carlo simulation reproducible, okay, yeah. So let me go back to the transparency, okay, yeah. Let me stop this screen and then switch back to the lecture slide. Yeah, okay. So the version 1 and okay. So you can read the version 3 code, okay, and then it should be quite very transparent, okay. So this is the version 2 code, okay. And then the version 3, okay, the kernel actually looks like this, okay. So you have to introduce this is the namespace CG or cooperative groups, okay, and synchronize all threads in the grid, okay. And then you can just call this one kernel, okay, right, and 2 kernels, okay. You can put the updating all even spins and all the odd size, okay, all odd size and all even size, okay. Yeah, put both of them at the same kernel, okay. You see there's a command here, cg syng, okay. So this is the cooperative yeah, so this is the global synchronization, synchronize all threads in all blocks, okay. So that is the action, okay, yeah. Okay. So this is the version 3, okay, yeah. Okay. Yeah, but there's some limitation, okay, yeah. So for the cooperative groups, okay, yeah, you cannot have the size, okay, is too, I mean the block size could not be too large, okay. And you have to then you may need more than just one grid, okay. So yeah, so there's a remarks here, okay. So I think the version 2 is the most I think yeah most should be most suitable for most purpose, okay. You just have to put the updating of the even size in one kernel and update all the odd size to the one kernel. Okay, that's it. Okay, there's a constant memory I already talked about, but then you can see, okay, for the device query, you can see there's a 64K of this constant memory. So this constant memory is for putting the constants, say for example, pi, yeah, at e, okay, and all these constants, okay. So for the constant memory, you have to declare this in the beginning, okay, constant int, okay, of this fw, bw, okay. Declare is a constant memory, and then yeah, I already showed you this, okay. Copy this data, this constant array, okay, from the host to the device here, and then you will be stored here as a constant, okay. It will not be changed, okay, in the entire simulation, okay. So, but it's very fast, okay, very, very fast. So it's good for the constants, and these constants are frequently used, okay. Yeah. So the next thing I would like to talk about is the error estimation, okay. Yeah. In Monte Carlo simulation, say when we talk about this one-dimensional integration, okay. So every time I generate a new configuration, okay, yeah, and that is completely they are statistically independent, okay, because when I generate a new configuration, okay, then I that new one, okay, is not related to the old one, okay, because I did not use the Metropolis, okay. If I do not use the Metropolis algorithm to generate the new configuration, then using, say, yeah, for example, the heat bath, okay, yeah, then these two successive configuration are statistically independent, okay. In that case, okay, the error estimate is quite standard, okay. Yeah, we can just use using the central limit theorem, okay, and the distribution of the mean, okay, obey the Gaussian distribution, and in the limit when n go to infinite, then with the variance, okay, yeah, sigma square, the mean value of the O, okay, will be this, okay. Yeah, you can check this, okay, by making the simulation, okay, independent configuration, okay. Yeah, and then you can check this the variance, okay, actually satisfied. It is the satisfy this relation, okay. Yeah, the mean, okay, the variance of the mean, okay. Yeah, so the variance of mean actually is equal to the 1 over n times the sigma of the observable, okay, itself, okay. Yeah, so that means the error, okay, is easily can be estimated 1 over square n, and then this is the standard deviation of the measurement, okay, and then taking a square root 1 over square root n would be the expected error of the mean, okay. So this here can just put it here, okay, as the error estimate. Okay. You see, so if you have a set of statistically independent configurations, then you can use this set of configuration to get a mean value, and then to estimate the error of the mean. This is the mean you get, okay, is according to this formula. Okay. So you see, you have the n measurements, okay, you have the okay, and then this you can compute this, okay. So this is the variance of the O, okay, of the observable, okay, and then divided by n is the variance of the mean, okay, mean value, okay, and then taking the square root, and that is the error, okay, of the mean, okay. So there's a very simple and guaranteed by the central limit theorem. Okay, this is the error. Okay, yeah. Provided all these configurations are statistically independent. Okay, but for the simulation or Ising model, okay, since for example we use the Metropolis algorithm, then in the Metropolis algorithm, okay, each new configuration, say once you change one spin, then presumably there's a new configuration. And this new configuration depends on the old configuration. You see, uh, at each side, okay, I flip the spin. The new spin, okay, is always opposite to the old spin, okay? No matter what algorithm, no, it's a sampling algorithm you use, okay? You can sample it, say, using a random number, okay? If bigger than 1/2, spin up, and then less than 1/2, spin down, fine, okay? Yeah, but then this is when you do the acceptance, okay, then you have to compare the energy, okay, between the old spin and the new spin, okay, the new configuration, on the old configuration. So your updating, your acceptance, okay, depends on your old configuration. So that means there's a correlation between these two configurations. Okay, no doubt about it. Okay, and this correlation means that I generate a new configuration. That configuration not statistically independent from the old configuration. So you are generating a set of configuration. They are not statistically independent, and they are correlated. Okay, and this will introduce additional error over this. Okay, so there's an extra factor, okay, of the error due to the correlation of these configurations. Okay, in this sequence of simulation. Okay. So now the question is, yeah, was it okay? So the answer is this. Okay, so if in a Monte Carlo simulation, if the CK are not statistically independent, then the error or the mean, okay, have to correct it by this correlated autocorrelation function. Okay, C. Okay, C. Okay, and this is the C1, C2, and so on is the separation of these configurations. Okay, in the sequence. Okay, so this OI is the measured with the I configuration, and O of the I plus M is the measured with the I plus M configuration. And these two configurations separated by M steps, okay, M in the sequence, okay, yeah, M configurations in the sequence, okay. So this is the CM. That's how we define CM, okay. So these two observable product expectation value, okay, that means I here and they are separated by M, and then I shift I, and then shift the, okay, I changing, but then the OI and OI plus 1, the separation, okay, are always separated by M steps, M configurations, okay, intervals, okay, yeah. So this is the separated by this M, okay, yeah, and this defines the CM, okay. So when you changing M, sum over all the M, then you can compute this expectation value, okay. And also for the OI, yeah, expectation value, then you measure all the OI, and then you get the expectation value, okay, the mean value, okay, in this case, okay. So similarly for the OI square mean value and the OI, yeah, mean value square, okay. So you can see when the M is equal to 0, then the C0 is equal to 1, because M is 0, then the OI square. And upstairs and downstairs the same, okay? So it's 1. But and if when M is getting very, very large, okay, then these two are not correlated, okay? And this is the same as the OI expectation value times OI expectation value. Okay. In this case, upstairs will be 0. Okay. Because this is the OI, when these two are not correlated, M is the big enough. Okay. Yeah, where they are separated very far away, then these two configurations, yeah, most likely uncorrelated. In that case, then the product of the expectation value will be equal to the expectation value of the product is equal to the product of the expectation value. Okay, so there will be a OI expectation value squared, and that is the same as this. So it is almost it will be almost 0. Okay, yeah, when this turns out to be very close to this number, and this will be very small. Okay, yeah, it could be even less than 0. Okay, yeah, but then when it's less than 0, then you don't have to cut. You don't have to worry. You don't have to you should terminate all this. Okay, if it's less than 0, then you should not put into the summation here. Okay, because CM, okay, I only need the bigger or equal to 0, but not less than 0. Okay, yeah. Okay. So the summation will be terminated at some point when the CM is sufficiently small. Okay, never negative. Okay, yeah. Okay, yeah. So how do I derive this formula? Okay, it's straightforward. Okay, but yeah, so I can just do the calculation here. Okay, yeah, and then I can derive here. So this is the detailed derivation. Okay, so I would skip the derivation because I don't have enough time to cover it. Okay, so yeah, you just take it for granted. Okay, so so this is the derivation basically. Okay, is the delta A square expectation value. Okay, this is the A here. A here is the true mean value. Okay, true mean value. Okay, otherwise, yeah, when you sum over the AI, and then there's an expectation value, and that expectation value, you think you cancel this and you will be 0, right? No, this is the one you get in the measurement. And this is the true expectation value. This is the true value. Okay. Yeah. You don't know that yet. Okay. Yeah. Only when n goes to infinite, then this the one you get the average at front will be equal to this. So this is not 0. Okay. And this can be written as this. Okay. Easy, simple algebra. Okay. So and then this also do expansion that get this. Okay. Yeah. So this is just a simple algebra. Okay. Yeah. And then the detailed derivation is here. Okay. Yeah. Yeah. I don't bother to go through all of them. Okay. You would take about 10 minutes to 15 minutes. Okay. So you can read it. Okay. You have any question? Let me know. Yeah. So the finally, okay, I have this. Okay. So this is exactly the formula. Okay. Here. Okay. So you can just take this formula for granted and then use it. Okay. Yeah. So this can be written as this. Okay. So this formula here. Okay. It's just the rewritten by this one. Okay. Okay. So okay. This. So this is the one error of the mean. Okay. If all of them are statistically independent. Okay. Yeah. And here, this should be n, okay? But usually you put n minus 1 here, such that when n is equal to 1, then error is go to infinite, okay? Because when n is 1, you don't know the error, okay? Okay. You only do one measurement, okay? You never know the error, okay? So, yeah. So this is so really doesn't matter when n is big, very large enough, the n and n minus 1 actually makes no difference, okay? Here is the error due to the correlation, autocorrelation of the configurations, and the configuration are not statistically independent, okay, due to the simulation algorithm, okay. The estimate of the CJ here, the autocorrelation, can be written as this, okay, and or this, okay. So there's a two different way of doing estimation. Actually, they turns out to be compatible, okay. So, yeah, you can see, okay, this is the when I changing a and the I plus j, then I can use the AI to do the expectation value, and also using the AI plus j to do expectation value, okay. So here is just use the AI to do the expectation value, okay. Yeah, and then yeah, downstairs are the same in both cases, okay. Here the I is just suppressed here, okay. Actually, this is the I square I, okay. So I have the sample code, okay. This or this is provided, okay. So using this, you can get the error estimate, okay, with this due to the autocorrelation. Okay, yeah. Let me finish this before I go to the sample code. Okay, yeah. So this is the code fragment to implement the scheme A and the scheme B. Okay, yeah. And okay, this just rewrite what is given earlier. Okay, so I don't have to worry about it. And there's another way to do the estimates, the binding. Okay. So if I have done the measurement for some, then NB. So I have the total measurement, okay? But then I broke the measurements into 7 binding, okay? Bind them into several blocks, okay? Yeah. So this NB is how many successive measurements of AI to form a block average BI, okay? So I have done N measurements, okay? But then I just bin them, okay? So NB successive measurement become one block, and then average it, okay, to get the block average, okay? Yeah. And then I can change the block size, the bin size, okay? And then the error estimate, I just use the block average to do the error estimate, okay? Yeah. When I change the you see, when I change the block size, okay, then this error will change also, okay? So I just estimate the error of the mean from the block averages, okay? So the idea is to measure the variance of block averages, okay, for several different values of NB. NB can be changing from very small to very large, okay? Okay, and in doing this changing, then I observe this error also change, and if you saturate, okay, I call it plateau, okay, plateau, okay. When I go from the N changing the NB, okay, then I take the plateau value, as the estimate of the error of the mean. Okay. So this is also very simple. Okay. And this is usually what I use in practice, because if I don't have the very large number of measurements, okay, then binding is the most reliable way to get the estimate. For the autocorrelation, I need a very large number of measurements, okay, because I need to get the autocorrelation CT to be very small, okay, and that requires a large number of measurements. But for the binding, okay, I can always do the binding, okay. Yeah, even the number of measurement is small, okay. So, so let me do the demonstration. Okay, let me switch to the terminal. Okay. Okay. Now, yeah, in using 2D, okay, there's a subdirectory called the autocorrelation. Okay. Yeah. Yeah, I will update the code inside. Okay, so you don't have to worry about the code inside at this moment. Okay. Yeah. So so this is the auto B. Okay, so using the B method to do the auto correlation estimate. Okay, so now there's an input data here. Input data. Okay. So the input data has three entries. Okay, the first entry is the energy. Okay, the second entry is the kind of monetization, and then the third entry is the some other observables. Okay, I don't have to specify or tell you at this moment. Okay. Anyway, this is the engine for the simulation. Okay, and this system is quite similar to the Ising spin system. So okay. Now I want to get the autocorrelation or the mean and the error of the first measurement. Okay, the data in the first column. Okay. Yeah, so let's look at the B. Okay. Okay. Auto TB. Okay. So this can be compiled with the G++ and the okay here. So the first just the with the data, okay, with the say number of measurements, how many measurements you read from the data file, and then what's the Tmax for computing the integration. Tmax, okay, is the maximum the sum of the I mean how many what's the M, okay, you have to consider. Okay, so you have to M has to be enough such that okay you can see the CM, okay, is become very small. Okay, so to become very small actually here means the say 10 to a minus yeah here 10 to minus 12. Okay, so if the this correlation, okay, the CM, okay, is less than 10 to minus 12, okay, then I will stop terminate the summation. Okay, because that means the furthermore, okay, that will the CM would be small. Okay, and CM even would turn into negative. Okay, so then it's not irrelevant. That is not relevant for the estimation of the autocorrelation error. Okay, so okay. So the computation of the autocorrelation, okay, is this, okay. I have the AI and AJ, and then this is the correlation of the AI and AI I plus T, okay, yeah. So and then the input file here, input T, input auto T, okay. So so there's I only I get this 8192, okay, measurements, okay, and the M, okay, maximum M I consider is the 2048, okay, but long before it reached the 2048, okay, the CM already small enough, so I don't need to worry about that, okay. But anyway, I just put a larger M, okay, so that it will not echo, say M is not big enough, okay, because the CM may not be saturated. That means CM may not be small enough, and then the series, okay, has not terminated yet. Okay, so I have to keep on acting the non-vanishing CM, okay, in order to get the correct estimate of the autocorrelation error. So the input data has 3 columns, okay, and now only look at the mean and the error of the first column, okay, and there is the energy, actually, energy density. Okay. So B, auto T, okay, okay. Now you see, this T now it runs up to 100, okay, before it becomes CM becomes small enough. CM go up to 100, okay, and this is the tau integrated, okay, and then the error, okay, is the this, okay, this factor, extra factor is this, okay. So with this extra factor, then it give me the correct estimate, okay. Otherwise, okay, the naive estimate, if you regard all of them are statistically independent, then the error will be factor 4 smaller, okay, and that's incorrect, okay. So this extra factor 4, okay, to multiply the naive estimate of the error, and then the standard deviation divided by square n, okay, times this factor, I get this error estimate, okay. So yeah, let me use another method, is the binding method, okay. So let me look at the binding input, okay. So the binding input is this, okay. So it's the input data, and then the again I use the same number of the measurements, okay. And then the bin size, I use 13 different bin size, okay. So the bin size 1, so the number of bins is so this is the 2, okay. This is a 4, 8, 16, and so on, okay. So the bin size is getting 2 to the power m, okay, yeah. And this is 8192 is the divisible by 2 to the power m, okay. So when I increase to 4096, okay, then I only have the 2 measurements, okay, the bin size, the size, okay, because this times 2 is 8192, okay. So this is the bin size, okay. So when the bin size is 1, then the number of blocks is 8192, okay. When the bin size is 2, then this is the 4096, okay, yeah. So and then from this different bin size, I look at the error estimate using the block average. Okay. And then from that, I can estimate what's the error. Now, let me use a printing and then the input printing. Okay, you see? Now, this is the data from the reading the input data, okay? And the number of data entry I read from the data file is 8192, okay? And then how many bin sizes? 13 bin sizes, okay? And then the bin sizes, okay? So you see the bin size and then the number of blocks, okay? Bin size and this number of blocks. And this is the block average, okay? Block average is the same, okay, no matter, yeah, block average of the blocks, okay? The mean of the block averages is always the same, no matter what's the bin size and the block size. But then the error is different, okay? The error is according to just the central limit theorem, okay? Yeah. So when the bin size getting larger, then the error, okay, would, I mean, it would be more or less statistically independent. The block average will be statistically independent, okay? So that means the error estimate from it, okay, would be the correct error estimate, okay? Yeah, but then you can see, okay, initially it was the small, okay, yeah. But when I increase the block size, the error also increased, okay? And then it increased up to some point, okay, it reached more or less like a plateau here, okay? Okay, and then these two, okay, almost the maximum here, right? Okay. So I would, if I look at the changing of the binding error here, the bin, then the saturate around 2 times 10 to minus 5, okay? So I would take this, okay, take this mean value, and then this error as the error, okay? So this error, of course, is bigger than this, okay? Bigger than this by a factor of 4 or something like that, 4 or 5, okay? Between 4 and 5, okay? So this exactly agree with this autocorrelation estimate, you see? Okay. So I can use this binding, okay, to get the correct error estimate, okay? Just the plateau value, okay? You can see this 1.6, 1.7, 1.6, okay? So this is more or less so I would say, okay, 1.6, 1.7, reach high and then go lower, okay? Then I will take this one, okay? It is increasing, okay? And then increasing to the maximum here and then decrease again and then increasing, okay? So usually I would just take it at the point when it is decreasing, then the previous one, okay, I just take this one. I will take this one as the error estimate. You can see this one is exactly consistent with this error estimate from the autocorrelation from some of the CM, okay? You see? So in both way, okay, you can get the correct error estimate. Okay. Yeah. So in doing the Monte Carlo simulation of the Ising model, okay, yeah, you should get the measurement data, okay, of the energy and the magnetization, okay, whatever the interval, okay, separated, okay, for your measurement, fine, okay, and then you can still have to go through the error analysis, measuring the error, okay, either using the autocorrelation or using the binding method, okay, and then these two methods should give you the consistent error estimate, okay, yeah. Yeah, suppose you may have made 8192 8192 measurements. Okay, if you do the you regard all of the configuration as statistically invariant, you will say you end up with the error like this. Okay, but if you do the binding analysis to take into account of the autocorrelation of the configurations, then you will get the error estimate is this 1.77 times 10 to the minus 5. Okay, it's 4 times bigger than the naive estimate. Okay, yeah. Or you use the autocorrelation, then you still get the factor 4 larger error estimate than the naive estimate. This is naive estimate. Okay, if you regard all the configuration as statistically independent, then this is the error of the mean. And after you take into account of the autocorrelation of the configurations, then you have this extra factor 4 multiply this, and you get this. Okay, yeah. And this is exactly agree with the binding, using the binding method. This is the per 2 value. Okay, 1.77 times 10 to the minus 5. Okay, so that's the error estimate for the Monte Carlo simulation. Okay, with the statistically not independent, or this or have a correlated configurations. Okay. Yeah, you have to read the transparency. Okay, the slides. Okay, to go through all the details. Okay, say for the derivations. Okay. Or yeah, if you don't go through the derivation, then you have to take it for granted of the using the formula to do the error estimate, and then use the sample code to do the error estimate. Okay. Yeah. Any questions? Oh, by the way, next week I'm going to give a seminar at the same time. Okay, so I could not give the lecture next week. Okay. Yeah, I'll go to the UC Berkeley to give a seminar at the same time, so I cannot give the CUDA lecture at the same time. I will make up the lecture later. Okay, so the last lecture will be the June 3rd. Okay, the Monday. Okay, so next week we do not have lecture, and then the following 3 weeks. Okay, and the last lecture will be the June 3rd. And June 11th will be the due date of all the problem sets. Okay. Yeah. I will make an announcement about the lecture of the next week. Okay. Say it will be postponed. Okay. And it will be make up. Okay. At the end of the semester, say June 3rd. Okay. Yeah. Yeah. Any questions?
老师，我可以问作业期的问题吗
Yes.
那个老师，我想请问一下，你作业期当中的 weight function， 它里面的定义是 c 的 exponential 负 a_xi， 那个 c 你说是一个 normalization constant， 这个 normalization constant 是指说我要为每一个 weight function都用那个 RNG sample 去 sample 一个随机数出来，然后并且把它们做 normalization。
我没有听清楚你所讲的这个 normalization 还是 renormalization 还是怎么样？
就 normalization 就你的作业的原文就写 normalization constant c。normalization
constant c 是哪个作业？是哪个？
作业期第7个作业。
第7个作业 ，OK， OK， the latest one， OK， 好 ，let me go to problem set 7， OK， yeah。Oh, here, okay, yeah, okay. Here, the C here, okay, you're saying the C here. The normalization constant, okay, yeah. Yeah, you can determine it, okay, yeah, fine, yeah.
所以这个 C 也是我们自己设定的，是不是？
没有 the normalization constant, you see, since W is the wave function, okay? So integrate all the wave function, okay? Integrate the wave function from 0 to 1, and then over x1, x2 to xn, okay? That should be equal to 1, right?
Yes.
After that, then you can determine the wave function, right?
Yes.
Okay. So actually, if you integrate from 0 to 1 dxi, okay, you normalize C to be 1, then since each is a product, okay, so it will end up to be 1, okay, then you must satisfy the integral of the all the x, okay, x1 to xn, all of them is from 0 to 1 is equal to 1, okay? You see?
对，
So this is just a normalization. That's what it means, okay? It's easy, okay, right?
老师，所以你的意思是指说，我需要确保这个 C 能够使 weight function 从
Yeah,
要等于1这个意思。
Yeah, right.
哦，
Okay.
没问题。
Otherwise, 你这个不可能是一个 wave function 啦 ，OK？
哦，好 ，OK， 谢谢老师。
这个就是whatever 你实际上 whatever 你 use 的话 ，OK， 你只要 normalize 它 such that OK， 它是一个 wave function 的话，然后你 insert 进去之后，你这个after you change variable 之后，就是你跟 one dimensional 那个 integration 的这种是 similar 的，对不对？只是我现在是 10 dimensional 而已。OK，
嗯哼，这个意思我知道了，这个意思。谢谢老师。
Okay, good. Yeah. Any other questions? Okay. Yeah. Anyway, if you have any other questions, okay, just send me the email. Okay. Yeah. So, yeah, I will update the sample codes later. Okay. Yeah. Especially the autocorrelation ones. Okay. Yeah. And yeah. Okay. So yeah, I will see all of you say 2 weeks later. Okay. Yeah. Okay, bye-bye.
Thank you very much. Bye bye.
Bye, teacher.